Good. So maybe in 1 minute we can start. Hello, everybody. For those who were not in the first part of this session, and now we will have an invited talk by Claudia Felser from MPI Dresden, and Claudia will talk about topology and chirality. And please, Claudia's 30-minute talks and then 5-minute discussion.
Okay.
Please.
Thank you, Vincent, for the kind introduction and thank the organizers for the invitation. So I choose a little bit unusual talk. I want to talk about some results I normally don't talk, which maybe can inspire new possibilities for new devices. So I avoid a bit Fermions, but you learned already a lot of Fermions, but I stay with the same space group in the second part with the B20 structure. So maybe there is a good way to get some interesting stuff out of non-magnetic and magnetic. And I'm sure there's also a lot of topology in the magnetic ones, as recently was shown in the paper from Christian Fleiderer in Nature. So now I have to try and, okay, yeah. So, that there's topology everywhere is not surprising, since we now know we have from all the 250,000 known compound after this extensive work of many groups that more than 25% of the compounds are topological. Even more if you take excitation and doping and things like this into account. And recently there was already first steps in direction to include magnetism, which is interesting for this community, for sure. So now all the magnetic space groups are also characterized by their topology, and so we have good possibilities to find interesting stuff there. So I think the nice thing is of topology, and for me, is that before we took simply band structure as a black box, and sometimes we got a value out of this, like the anomalous Hall effect and so on. And now we already see from the band structure very often what is interesting, or can we expect interesting properties of the compounds. And not only if we see semiconductors and think about maybe quantum effects in the semiconductors, or see a nice Van Hove singularity, it's many possibilities where bands are crossing or degenerated, like you can hear. So we can already see, if we see the band structure, whether there's something interesting to expect it or not. And this is not only because of the band structure. Sometimes we need more special calculation, because very often also there's a boundary corresponding, and so the topological materials have interesting surface states, and this area, I would say, is also not really fully explored. And on the other side, sometimes we go beyond the simple band structure and look for the phase, like in Weyl fermions and the Chiral fermions I want to talk today also. Okay, so the whole story started with the topological insulators, and one important ingredient is where we are looking for is a band inversion, but this band inversion is quite common. So we have a conduction band and a valence band in this, what we see here in this three-dimensional plot. And then we might have this, or we have this overlapping area, the so-called nodal-line. And depending on the symmetry consideration and spin-orbit coupling, so this can be a forbidden area, so forbidden crossing area. And so we end up with a band gap again. So then parts of the conduction band and the valence band and vice versa. And because if we have special conditions for the symmetry of the band, we get the surface states which connect the valence and the conduction band, and they are topological protected. And in a topological insulator, they are all over the place. So the whole crystal has this topological surface state. But there is very often more symmetry in the crystal, and then we might have bands which stay connected, so they are maybe protected by chirality, by rotation and so on. And so depending where these connected points are, whether they are at high symmetry points, we have Dirac semimetals. When they are at low symmetry points or in magnets, we have Weyl semimetals. And these Weyl semimetals are especially interesting because they have the degeneration points have chirality, so they are distinguished different from a Dirac point. So this is a doubly degenerated point. And since spin and momentum is locked, the electrons here are distinguished from there. And we have a very flux between these two kind of reciprocal space momentum magnetic monopole. And so this leads to very special surface states which connect these two points in the bulk, and this is the so-called Fermions. So why are super excited about this? Because I think so the Weyl equation is a very special equation. It allows for a chiral anomaly, which is also a hot topic in high energy physics, because it might be an explanation for the origin of the universe and the asymmetry between particle and antiparticles, because this is an anomalous non-conservation of a chiral current under certain circumstances. In a vacuum state, for example, you can have an asymmetry between an elementary and a particle and antiparticle, and this could explain that the universe exists with more particles and antiparticles, so we are existing. So we cannot do this directly, but we can simulate this by assuming quasi-particle excitation. So in Dirac semimetals, and here the electrons and the hole plays the same role as particles and antiparticles. The velocity we are looking for is the Fermi velocity, which is for sure smaller than the speed of light. Anyway, so this is a really hot topic, I still think, and it's especially interesting in the context of the Weyl semimetals. So therefore, if you make synthesize the Weyl semimetals and we are synthesizing single crystals, this is more or less what we are looking for. We're looking for the Fermi arcs, which connect the two Y points. We are looking for the chiral anomaly, and the conditions here is that if the magnetic field and the electric field are parallel, you should see this negative magnetoresistance. This is simply the prediction by theory. And you can do, instead of a voltage, you can also apply a thermal gradient. And there was a prediction by Subir-Safdie. It's more or less the same like the chiral anomaly, a thermal chiral anomaly, that this reflects the actual gravitational anomaly in astrophysics. Okay, so in general, because of the Barry curvature, we expect also giant responses to external stimuli. So many of these Weyl semimetals have large Nernst effect at low temperature and other interesting properties. So simply to see this first simple example, so it's a family of niobium phosphide, niobium arsenate. They were grown. First, there was a prediction on the iridate, but this could not be realized. And with this simple material, this is a tetragonal unit cell, it was possible to realize the Weyl semimetals. You see here many Y points in the reciprocal space in the Bryan zone in this material. But they are quite close together, so it's always a challenge also then to see them in angles of photoemission. But this was the first thing what we did. We looked for the Y points in the material, so for the splitting of the bands here, which are related to the Y points, but the points are really artificial here. It's not a real measurement. But we saw that there was evidence close to the Fermi energy for Y points, and the splitting of the bands was enhanced if you made the material heavier. So if you want to say increasing spin-orbit coupling. And here you see the calculation of the Fermi arc and the measurement of the Fermi arc, and this was quite convincing, and people now believe really that this material is Fermion with the Fermi arcs at the surface. Anyway, to see transport properties is always a little bit more challenging, because there can be artifacts on one side, but also you really need the right band structure at the Fermi energy. So this is a challenge always. And here we tried it with niobium phosphide, because this was our most favorite material. And we were more or less lucky, because when Johannes got this micron ribbon, so this compound was simply autodoped by gallium via the focus ion beam fipping, and this autodoped the material to have the Y points at the Fermi energies. This we can investigate, because here you see measurement of the magnetoresistance in a field, and it's a positive magnetoresistance. And you see these wiggles here, which are quantum oscillation of the material. And from the quantum oscillation, we can conclude the Fermi energy. So we exactly know where the Y points are and what the electronic structure is. So, so this was then doped with the gallium to the Fermi energy. And the idea here was now to check the chiral anomaly by changing the direction of the current. This is a Hall measurement where we measure the magnetoresistance effect. Here's the magnetic field perpendicular to the current, and then we switch the direction of the magnetization, and we saw this chiral anomaly as predicted by theory. So it's in this nanorhythm, it stays there up to room temperature. So we think there is evidence for a chiral anomaly in this compound. The same, as I said, we can do then, this is the measurement here of the current with the voltage, and you can do the same now by applying a thermal gradient. And the prediction here from theory, from Subesat, Steff, and co-workers was that you should see a B-squared behavior at low fields, and this should turn around and go to 0 at higher field. And this was indeed exactly what we saw when we applied a thermal gradient at this nanorhythm. So this was already very interesting. So we looked for more, and this brought us even into the New York Times. So we look now for more nice white semimetals, and on this way we found a very nice band structure of tantalum selenium 8 iodide. So if you see here, it's like, it looks like nearly like graphene, but the interesting thing is that this point, this crossing point in the band structure is not at the high symmetry point, which is what is obviously visible. So we have grown the single crystals, but we were surprised that the single crystals was in some sense semiconducting. And then by looking into Ingerisov photoemission very carefully, we saw that the system has a charge density wave gap, and this was in agreement also with the literature at this time. And so we were first a little bit frustrated, but then we found a series of interesting papers which said if you find a charge density wave instability in a white semimetal, so this is a quasi-particle, you see it as a quasi-particle excitation for an axionic charge. An axion is a particle which is looked for or for explaining dark matter in the universe, and was not yet seen. So this was extremely exciting, but then it was also changed how to find out what to do to see whether this is really an axion insulator, this compound, and not simply a simple insulator. So this was a proposal. So we have a white semimetal, which is the DFT band structure. And if you apply, or because of the correlation effect, we have a charge density wave, and this charge density wave is then responsible for open up a band gap. So what we did here is then we tried to slide the charge density waves. This was also the proposal. And we did it again for magnetic field perpendicular to the current and for magnetic field parallel to the current. And indeed, you see an effect only in case if the field is in direction of the current, which was expected due to the chiral anomaly in the white semimetal and the axion behavior. So the other important point was that the distance between the white points should be exactly the nesting vector of the charge density waves. This was a little bit challenging to find out, but finally we also identified that this is exactly the case in this material. So it might be, I think, that especially systems which have Y crossings at the Fermi energy, which are very clean and have no additional bands with electrons and hole pockets, what you want might be very easily destroyed by correlation and go into such a charge density waves phase. So therefore, might be interesting to look for more charge density wave systems and look to whether there's a connection to axion, phasons, and white semimetals. Okay, then the next step was to add magnetism to the white semimetals. And this is very interesting because if you break time reversal symmetry, which means in case when we apply a magnetic field, for example, to Dirac semi-metal, we turn Dirac points into Y points. This is why Dirac semi-metals show similar properties as Y points. But the Fermi arcs and the distance between the Y points are not so large. But if you have an intrinsic magnetic field, like you have it in ferromagnets, so all crossings in the ferromagnetic band structures are Y points. So it's only the question how to get them to the Fermi energy, because the distance between these Y points can be much larger than if we simply break time reversal symmetry. So this is already done for a few compounds. So we did it for cobalt to manganese gallium. It was done before many things. And for cobalt 3 tin and gadolinium platinum bismuth was the first even example for us. I want to show here only one, and typical signatures of this white semi-metals, these magnetics, are also the chiral anomaly. Nobody measured the gravitational anomaly. We should do it. We didn't do it yet. And the anomalous Hall, and the anomalous Nerns as large responses in the magnetic field, and for sure STM and AlPt investigation to prove the Fermi arcs in this material. So we choose the cobalt 3 tin 2 sulfide 2 here, or I choose this also as an example because it has a very nice cargomine lattice, and cargomine lattice have super interesting band structures. The compound has a half metallic ferromagnetic band structure, and the spins are out of plane magnetized. So if I magnetize them once, they stay magnetized because they are hard magnetic. So it's even possible to measure and maybe magnetize crystals in AlPt. So the first thing what we did is really to measure the chiral anomaly. And this you see here. So you have a negative magnetoresistance if the B field is in direction of the current, and a positive magnetoresistance if it's not. And it has really the Y points, and it has also a very simple band structure. As I said, it's a half metallic ferromagnet. You see only one spin direction. If spin is a good quantum number, it's not in case of spin-orbit coupling. But anyway, so at the Fermi energy, because this compound, it's a shantite, it's even a natural compound, has a semiconducting relative with 1 electron less. So it's simply you fill in 1 additional electron, fill 1 band. This crossing bands, these 2 crossing bands half, and then you get this nodal line if you have no magnetic field. But if you apply magnetic field, if you magnetize your crystal, you see then this Y points, which are, you see, much far from each other compared to the neop and tantalum arsenic, and on top it's very close to the Fermi energy. So this then you can verify by AlPt, and we did also STM measurements. So this was predicted Fermi arcs. They are nearly 30% of the Brilliant zone, and you see they are nicely seen in the ingress of photoemission, and the Y points are slightly above of the Fermi energy, which you see in this upper part where you can compare here you can compare the ingress of photoemission data with the calculation, and then therefore we doped the surfaces with potassium to just move a little bit the Fermi energy, and then you see we even can see in the AlPt data, in the ingress of photoemission data, the Fermi, the Y points below the Fermi energy in this compound. So another thing is because of the crossing points in the band structure, we can calculate transport properties. And this is via Kubo form. We use the Kubo formula, but we and the Berry curvature, and we calculate the transport properties for different materials. But we can also do a toy model calculation. This was the first step, and this shows that if you have crossing points at the Fermi energy and apply a magnetic field, and so we see that the Berry curvature is enhanced around the Fermi energy, and this leads to enhancement of the anomalous Hall conductivity and also to an enhancement of the anomalous Nernst conductivity. So the anomalous Nernst conductivity is the first derivative of the Hall conductivity, therefore it's much broader distributed around the Fermi energy. So this is also what we see in the experiment. We find a large anomalous Hall conductivity in this material, and it shows a nice big hysteresis because of the hard magnetic behavior. And if we put it into the scheme of Naragoza and Tokura, where they distinguish whether the anomalous Hall conductivity comes from the Berry phase and is really intrinsic. So we see that in this material, we have an intrinsic, mainly intrinsic contribution to the Berry phase. So the same as the agreement between calculation and measurements are also very nice in case of the Nernst effect. So you see a large Nernst effect, and since the material is hard magnetic, you see even in a zero field a Nernst effect, and you can switch the sign of the Nernst effect by switching the magnetization. So if you compare this now, the Nernst effect versus magnetization, so it was believed for a long time that this goes linear with the magnetization. And this is the case for many materials, but you see all these topological materials, I cannot talk about all of them, they show this unusual behavior. So, and then we looked at edges of this material because we recognize that the anomalous Hall conductivity per layer is nearly close to the quantized value which we expect, and this was motivating us to look with STM at the edges of this material. And if we apply bias, we really see a quantization of the edge states of the compound, and this might be related because if you do a toy model calculation again, so if you calculate the anomalous Hall conductivity between the 2 points, this would be exactly the quantized value. So if you then would be able to move even the Y points to the edges, so makes this a topological insulator, then you would see the full quantum anomalous Hall effect in this material. So the question is, can we see this in this material? Okay, and the last part I want to talk about this new fermions. They are crystallizing here in the B20 structure, but there are also chiral superconductors in this new fermion. And this new fermions means, despite of the 4 times degenerated point in the Dirac points, we have, for example, 6-fold degeneration in this new fermions. And but we can also here, in case of this crystal fermions, we have even an interesting feature. They are not, if they are chiral, the crystals, they are not at the same energy. So you see the Fermi Y points at different energies, and this is very interesting also for optics. And they have interesting surface states. So what we do if we go to chiral crystals, we combine the interesting properties of a chiral crystal and what we know from topology, or this nice Berry curvature effect. And the result is that we get, for example, here are typical examples for how it is. For example, you have at different points in your Bryan zone, the chiral Y points, and the expected Fermi arcs are giant, and they are also chiral. While the electronic structure, the band structure, cannot be distinguished from 2 enantiomer of a chiral crystal. And the fact that we have the points at different points in the Bryan zone allows us also to distinguish them in the energy around. They can be at different energy. So we were able to grow 2 of these compounds, and the compounds are very familiar to many of you because it's manganese silicon and iron germanium belongs also to this compound. From palladium gallium we could grow 2 different chiralities of the crystal. This was hard work and a little bit of luck. So where we have really can then investigate the difference in 2 enantiomers. So this is the electronic structure. So we have one 4-fold degenerated point at the gamma point and the 6-fold degenerated point at the up point. And they belong to the unusual class of a large Chern number, which was not investigated before. And here you see how the electronic structure looks in the 3-dimensional space, even by including spin-orbit couple. So we have 2 different chiralities in the crystal structure, but the band structure is just the same. But we can assume that the Berry phase, so the electron momentum, which is locked here, has different chirality. So one time it should have this chirality, and in the other case it should have that chirality. And but we cannot distinguish this in a simple band structure. what we can distinguish is the resulting fermions, because the fermions are chiral. This is already, I think, amazing. So the band structure is not chiral, but the fermions are chiral. So, and this is what we could easily investigate by photoemission. So we did photoemission, and this is this fantastic work of Niels Schröter. So here you see the fourfold degenerated fermion, and here's the sixfold degenerated fermion. Then you see the fermion. Then you see this round Fermi surfaces, and around the round Fermi surfaces, you see this Fermi arcs, which are distinguished between really distinguished. You see the difference between the. I hope you see the difference between the two chiralities, two enantiomers. So which means so we have the same band structure, and we can say, okay, we can see the Berry phase, different sign of Berry phase here in the band structure via the chirality of the fermions. But is there a better way to, okay, and then the second point, what we wanted to find out is, can we really see these large Chern numbers, which is larger than in simple white semimetals with the Chern number +4, and indeed we can do this if we go to compounds which have a large spin-orbit coupling. So you see then a splitting of the Fermi arc. So you see that every Fermi arc is 2 times degenerated, and this corresponds to the Chern number of 4. So you see also, this was a prediction by Joel Moore and co-workers that you should see very special photo galvanic effect. So if you shine circular polarized light on this, so the circular to galvanic effect should be quantized, because the white points are at different energies. And if you are able to only occupy one of the white points, then you should see a quantized plateau. And there is some evidence in the measurement of Joe Ehrenstein done on rhodium silicide crystals, where he thinks we really see the Chern number and the plateau in this compound. Anyway, so trivial bands always are a disadvantage for this and should be avoided. Okay, so you can do this with other compounds in the family. This family is quite big, and as I said recently, so there were even Haas van Alphen investigation on manganese silicon from Christian Fleiderer, published in Nature, I think 1 week ago. Okay, so but can we we can see the Berry phase, as we know from the anomalous Hall effect in magnetic systems. So we could look for the Berry phase character, the sign in these chiral materials, and for every band. And there's a Berry phase here. We looked along the 1-1-1 direction, which is the gamma to R direction, which is the most interesting direction for us. And there is even a strong relation between the Berry curvature and the orbital angular momentum. And this was our motivation to look for the orbital angular momentum for these 2 compounds which we have. And this we did here. You see also a very nice asymmetry of the orbital angular momentum. These are unpublished results, and for the orbital angular momentum, one has to be very careful, because not to imprint by the chiral light this orbital angular momentum, but this you can then remove by treating the data correctly. Okay, with this I come to my summary, and I think I was in time. So I hope I give you some new ideas for thinking about new devices. So because more or less we can see most of the inorganic compounds through the eyes of topology. So we have the paramagnetic white semimetals, which have this fantastic, interesting chiral anomaly. So it's a violation of the parity. So this is for me one of the super exciting things. And in the magnetic ones and in the new chiral ones, we have this very strong Berry curvature effect. So this might be very interesting to understand maybe chirality in nature also a little bit better, but it's also interesting to rethink and think about the relation between real space and reciprocal space Berry phase. I think there must be a connection now. There are more and more connections coming out. And for the future, it was the starting point already with manganese silicon and with the fermions to combine chirality and topology and magnetism, go beyond the single particle picture you saw already in the axions. This is an interesting direction, and maybe oxides are the direction to go. And for us, it's also to connect orbital angular momentum spin, angular momentum and Berry curvature to even have a better description of the materials by angles of photoemission. Okay, and I think it could have impact to spintronics. Thank you very much for your attention. This work was done with a lot of fantastic collaboration, and I especially have to mention Johannes Goth and Nils Schröter, and you will learn from Maya, I'm sure, more about quantum chemistry, but sometimes old guys like Jürgen Kübler are also extremely helpful, and for sure I thank all the co-workers, other co-workers in the area of photoemission, etc. Thank you for your attention.
Thank you very much, Claudia. Again, very nice, very rich and inspiring presentation. Thank you. I think we have one question already. Please, Shaija Sharma, can you unmute and ask the question?
Hello, ma'am. Ma'am, I have a question. You showed for the anomalous Nernst effect that with change in magnetization, you can turn the sign of Nernst effect from positive to negative.
Yeah.
Is this any such a kind of relation for the normal Nernst effect where we can see the sign change from positive to negative?
Yeah, you see it, but here, anyway, I said you can set it even because it's a hard magnetic material, you know.
Ma'am, this is for magnetic material. For non-magnetic materials, like normally for topological insulators, can we have a similar kind of relation for positive to negative Nernst effect?
Yeah, but you can have a negative because you measure the Nernst effect in a magnetic field. So if you switch the field, negative and positive magnetic. But here we can set it because if we switch off the field, the magnetization also stays because it's a hard magnetic material. This would not be by a non-magnetic, even they have also very nice large Nernst effects. It's true.
Okay, ma'am. Thank you.
Thank you.
Thank you.
Good question.
Is there another question? If not, I can ask one. You mentioned the interest to have a chirality, topology, and magnetism. In this last part of your talk, when you present results about palladium, gallium, for example, I didn't really get it. Have you been able to observe some topological texture in real space in this kind of devices?
It's the question whether I think there's only one paper now, which is 1 week old, and we have some data on iron germanium where they see nodal phases, even planes, I think, in manganese silicide. Okay. And the question is, does this reciprocal space topology influence maybe the real space topology, and is this maybe responsible for the fermions or influence or the non-collinear spin structures? I don't know. But I simply think there's maybe still a lot of interesting questions to ask.
And do you expect in this case to have like a, I don't know, new contribution or new component to the so-called topological Hall effect, for example, like gigantic topological Hall effect, or do you?
Because if you have in real space and in reciprocal space a very curvature, and the very curvature, yeah, I think there's a lot of, and I think they are also connected. Yeah, they must be connected, you know. So there should be something beyond. So I think this is where the theoretician maybe could even say maybe we can find some other interesting chiral things from astrophysics or from even realizing in this magnetic system.
Thank you. Okay, I don't see any other questions, so I can ask maybe a last one. At the end, you talk about the very potential interest for the application in spintronics, for example. So as you know very well, for this kind of application, we need thin films or ultra thin films. What is, in your opinion, the best among all the systems that you present today the best one for getting this extraordinary properties, but in thin film geometry or even heterostructures?
This is a very good question. I think that Toki Takanashi already works on cobalt 310 sulfide 2. The only disadvantage is here that the properties disappear at 150 Kelvin. Okay, so you want to have it at room temperature. This is one point. Okay, so but then the Heuslers are better, but and they're well known. And yeah, so the question is, can we have 3D quantum anomalous Hall effect in compounds even at higher temperatures? This is a super interesting question. And even for cobalt to aluminum, manganese aluminum, so Bin-Hai's group in Weizmann, they claim to get, or Bin-Hai with some people from China, they claim that the value is very close to the quantized value. But since we don't have Landau levels in the quantum anomalous Hall effect, we cannot really prove it. So there must be other ways to see whether this is really an interesting way to go, because at the end, to have a quantum anomalous Hall effect at higher temperature would be great.
Thank you. Sergio, you raise your hand. Do you want to ask a question?
Yes, but
okay.
There is another question in the Q&A. Maybe you can ask.
Okay, yes, sorry. So yeah, the question in the Q&A is, how does the Nernst effect in Weyl semi-metal get affected by lanthanide doping?
So I would say the Nernst effect should be namely related to the Berry curvature, and the Berry curvature relates to the to the electronic structure. So you maybe add or subtract electrons. This would make a change, but otherwise you have also flat bands, which adds again to the Berry curvature. So I think in total, I would say it should not negatively. So the Berry curvature, I would say, and the Hall effect is a stable effect, so it's not related to the cleanness of the sample. So I would say it should be not negatively affected, for sure. So whether it becomes larger or not depends from what is the influence of the substituted element.
Thank you. Sergio?
Okay, so maybe I can ask a question.
Yeah.
So in a couple of slides before, you show the photogalvanic effect, and so this one, the next one. So this is expected to be quantized, right? And then you have all this variation. I understand that at high energies, this is because of the two points, the Y points that are actually involved. Then at low energies, you see also big variation. Can you tell us a little bit about that one?
Yeah, there is a lot of discussion about the origin. So they might the influence of still too many trivial bands. So what we are looking now is like, the point is, I have the feeling, unfortunately, if you have a very clean white semi-metal like tantalum selenium iodide, you know, then you have the degeneration is easily lifted by a charge density with instability. If you have electron and hole pockets, this trivial band might destroy or negatively influence your properties.
How does that happen?
Yeah, so so this is normal. So in rhodium silicide, you have quite a number. I have somewhere the band structure. It's very similar. Look, you have quite a few more bands at the end point and so on. It's a lot of spaghettis. And if you look for photo effects, you look for the transitions, and you should have, the nicest would be if there would be only this point and that point, and we would only have transitions, and we maybe would have the quantization, but otherwise more or less, and even by lower energies, then other effects come back into account. So this is
that's clear. Yeah, thanks.
Thank you very much. I think we have to stop now. Thank you again, Claudia. There is this link in the chat box for the discussion. So you can, if you have other point to discuss with Claudia, you can go in this room. Thank you very much. And then the next session will start at there is a lunch break, and next session will start at 2 p.m. Thank you. Bye bye.